Understand the symposium you're having is debris flow impact forces on single and dual barriers. And unfortunately, I'm not going to talk about single and dual barriers or debris flow impact, but I'm just going to discuss about my experience on dealing with hazards, an emergency case, and then what can we do, and how emergent technologies can potentially help to understand and cope with these emergency situations. So you can see my title is Introducing Emerging Technology, Practice for Slope Safety. Now, you can see that in our field, there are a lot of excitement in terms of emerging technologies, starting from computer vision, LiDAR, UAVs, these aerial vehicles that fly drones. We've been talking about using satellite, which is INSAR, for monitoring the movements. And then my favorite is always distributed fiber optic sensing technology, embedding sensor for lifelong monitoring, implying that these fiber optics, which I'll talk about later, can last for many, many years because of the way the sensor is made. And then I know Gio, and we've been working together and looking at the opportunity for wireless sensor network. It allows continuous monitoring at difficult to access sites. And you'll see some of these technologies coming up. And in the past 10 years, we see a lot of these technologies being introduced in geotechnical engineering. And you can see that the precision you can go is within a sort of 0.1 millimeter to up to 20 millimeters, which is in the range that we're very, very interested in to understand the precursor, early warnings of the system. Of course, if it moves 10 centimeters or 20 centimeters, it's already finished in the sense that it's moving. But what we want to do is, can we see something that is gradually start to happen, and therefore we can cope with any sort of uncertainty that we have. And I'll talk about this later on. One of the site that I was involved, this was part of the court case that happened in 2014, also a landslide, and dealing with that. And I'm just going to tell you a little bit over what really happened on that particular event and how we analyzed, but then what really came out of that particular sort of a court case. So you can see this was also a landslide that happened in state of Washington on March 22, 2014. So that's about 8 years ago. At 10 o'clock in the morning, a major landslide occurred near Oso. 8 million cubic meter of mud and debris flow traveling approximately 1 kilometer, which I'll show you later on, spread all over the valley of North Fork, a river covering small community. So this particular community that existed at the toe of which is shown over here, was consumed by the debris flow and landslide. And then you can see the aftermath of that. 43 people were killed in making the deadliest landslide disaster in the US history. And then as we see that the event was preceded by a 3-week period of wet weather up to 200% of normal, meaning that, of course, as we know in geotechnical and engineering, groundwater did affect in terms of initiating the landslide. So one of the technology which we start to use a lot nowadays is LiDAR. So this is aerial LiDAR showing the topography of 2013 before the landslide happened. And if you see this particular one, this is the a cliff that it had. And then actually you see this particular material, which I'll show you over here, happened. There was a small landslide happened in 2006, Hazel landslide. And you can see the shape of it. And because of the LiDAR, you can see how it progressed at that time. There's a river over here going along here. And then there was a community which was over here. Now, there was a LiDAR scanning, obviously, after the slide. So this is 2014. So you can start to look at back and forth. Oh, sorry. You can go back and forth and see what's going on. Raymond, do you see my slides going back and forth?
Yes.
Yeah.
Back and forth. Yeah.
So you can see that this particular material actually here, it moved, but then actually the new material moved from this particular part, and then much larger mass moved and then spread downwards for about 2 kilometers or 1.7 kilometers. So it's a huge landslide, as you can see, consuming the community. This is one of the early days of our depth average simulations of the material. And you can see that we have blue, red, and green because there are three important materials that moved. And what really happened was that actually the first two material first, and after 25 seconds, the second one moved. So how and why the landslide can have such a long ground distance? You have to start thinking about scenarios, identity factors, gain insight in the mechanism. So that was what we were asked by the law case to think about how to deal with that. And there are a few characteristics like long run out. Oh, sorry, I misspelled over here. Run out, high velocities, it was like this one, and then short duration. Main event was about 100 seconds. And you can see how it moved from here over here. And you can see a nice scarp going over here where material have moved downwards. The details, you can read this particular paper by Albayero, who was a postdoc at that time and now a professor, assistant professor at Virginia Tech. And with my colleague, John Bray, run out evaluation, also landslide with a material point method. So we use a method called material point method, which we've been promoting, and many of you may have heard of it, and some prediction may have been used this method yesterday. Now, I show you the depth average, and then currently working on the 3D version of it, showing the proper 3D. But then at that time, we were pushed with time because of the court case, and we did 2D analysis, as many of us do. And you can see that there are three sort of interesting. This is a geological profile showing some yellow is the sort of a sand and gravel outwards glacial tilt material. And then you can see different materials. The green one is the glacial lacustrine deposit. It's clay with silt here. And then below that, there is a lacustrine deposit of sandy material. Now you can see from here that this particular material is another one, and which you see this particular plain is an ancient landslide. That means that this yellow used to be on top of it long time ago. And then actually there was an ancient landslide move over here and then stopped over here. So it does show that there was a history of landslide in this particular case. Now I mentioned about 2006 landslide that happened before, and that's this material that moved from here and moved over here in 2006. So that was one of the benchmark we used, and then trying to predict the other one. And you can see that there are three materials: debris material, which is over here, which is sitting on top of the river. And then there's M1, which is the material that moved in 2006. M2 is the one that moved recent at the 2014 one. And then this M3 is a new plane that moved. And so we did material point method, and this is the simulation, stage 1 and stage 2. Actually, stage 1 is when this two material on the ancient landslide slipped, potentially due to the groundwater coming to that ancient landslide slip plains and mobilizing that. And after 25 seconds, which seismic signal shows that this particular new flame plane was formed, and then it moves. Now, here we simulate it by knowing the failure plane, but which generated at that time. So we're currently working on modeling this a little bit more carefully to create how this shear plane is developed. But this one shows that there are two events happening. One is this particular one unloading, and therefore this one moved and then goes downwards. The question really happened is that whether this run out distance had an effect in terms of this M3, which is the big one. Did it push the original M1, M2 to go it further? Our simulation shows that it didn't matter. This particular M1, M2 had a large potential energy to start with, that it just moved all the way downwards. Now, this is a material point method. The one they show on the bottom is the shear strain, and you can see the localized shear strain developing. And you can see the rigid potato wall part that's being sort of sheared in red. And then, so you can see a blocky feature as well, which we simulate. And if you go back to the original picture of the slide, you do see these blocky features. Now, engineering-wise, it's really interesting, and we can do the simulation. I'm sure that prediction yesterday gave you a variety of interesting insights, and that's what we learned through these simulations. Now, if you look at actual site, you do see this particular slip plane going on, and you can see a lacustrine deposit. You will see always these laminar features, which you see over here. So geology is more complex, as we all know. That's why geotechnical engineers survive in engineering. And that's why we have our profession, to understand how we deal with this geological complex things. And the feature and interest is really when you do a direct shear test on these intact samples. Many of the samples will show a peak friction angle of 24 degrees and critical state of 22 degrees and cohesion of certain 100 kPa. But some specimens, because it's slipping along that certain plane, you can have a friction angle of 12 degrees, which is a residual friction angle. So natural soil structure is internal. How do you deal with this material in the field, and how do you cope with it? So there are a lot of uncertainty that we need to deal with. This is the also landslide that happened in 2014. But if you look at past 5,000 years, you do see a potential landslide that happened and show the geomorphology of what that happened, like Ronan landslide happened sort of at 500 to 2,000 years ago in a similar magnitude. But then the question is that if you're living only for your life for 100 years, what is your sort of risk? How do you deal with this risk? And tell your resident how to deal with it. That's a very difficult one. Now I'm going to another one. This is not related to landslide, but this is called wildfire. And in California, we're currently really into wildfire season coming in, and worried about what's going to happen during the sort of fall time, when it becomes dry and then fires start to happen. And this is a campfire 2018 Paradise that happened in November 8, 2018, 4 years ago. And there was I'll show you later on, there's a place called Paradise, which is over here, which has a population of 26,000. And then that particular fire happened and 85 people were killed, and then burned 18,000 single family. It means that all the houses in the Paradise, almost all the houses, as you can see here, were burned down. Oops. So this is the picture of the map of that particular town called Paradise. And you can see that Paradise has 26,000 people. And then there's a bigger city called Chico. And then the other one down here is called Oroville. Wildfire started over here near what we call Pulga. And then the fire propagated toward and consumed this particular one. Bear in mind, the scale is 2 kilometers. So this is about 10 plus kilometers, so 20 kilometers over here. And typically wildfire over here will gradually move and tell the resident you have to evacuate. But on that particular day, actually the fire happened on 6 o'clock in the morning, and by 8 o'clock, within 2 hours, it consumed, and 1 hour, it just went through all the town. So this is a time history of that happened. So you can see that Pulga is right over here, and this is where the fire started, and then this is the town of Paradise. The firefighters received a message that they see a fire on this particular one. So the firefighters in Paradise, when there's no road going from here to here, so they had to go down and then go up, and they put the command center over here to deal with that particular fire. So that is 6:30, and then so 7 o'clock, you start to see people moving along to cope with this particular fire. Raymond, do you see my animation?
Yes, we see that.
Okay. So this is 7 o'clock. So fire started at 6:30. You can see that by 8:30 it's consumed, and then by 9:30 it consumed all the paradise sort of area. So this is a simulation actually, but simulating the actual thing that happened. And you can see that that particular day, wind was so strong, the fire propagated so quickly. So think about you're in a residence over here, and then you wake up in the morning, and then you have to act quickly. What would you do? By 8 o'clock, sheriff ordered to evacuate Paradise, meaning that they did have, that particular town had what we call award-winning evacuation plan. They were award that they have a great plan for evacuation, what we call stage sort of evacuation, looking at different stages evacuating. Unfortunately, this particular one didn't work because the idea of evacuation assumes that the fire propagates slowly. But the sheriff have to say, evacuate everyone at the same time. So by 8:30, and they tried to say evacuate zone in 7 and 2, but then that was so difficult. If you see over here, so this is the fire that the sheriff had this small camera on his jacket, and then it shows what's going on.
Oh, that's not good.
So this is around, so you can see that it's 9 o'clock-ish, which is just when they start to see, okay, I got to do something. So by 9 o'clock, they said everyone to evacuate. They're all 26,000 people in that particular town. Now, people start to evacuate from Paradise, taking cars to go to 2 locations. One is Chico, and then the other one is called Orville. And you can see that people start to take certain roads, but fire came this way. So one of the roads were not able to be evacuated because the fire was consumed that one. Unfortunately, the cell phone network went down at 10 o'clock. So they don't have a way to use WeChat or other, in here we use other things like apps to understand Google traffic, to understand what's going on within, if you're within the Paradise. And then there was a traffic congestion, which is really congested over here, along all the way here, because actually these jurisdiction of Paradise and Chico were not able to communicate to change the traffic light over here at the entrance of the Chico, the town of Chico. And you can start to see some of the messages telling that how congested that particular road is, and people have a difficulty evacuating. So we went out the site, and then we start to look at what really happened on that particular day and try to understand what's causing. And that led to our understanding that we really need to start thinking about evacuation a little bit more carefully, not just planning. So we've been doing like wildfire modeling of how fire propagates, and we do traffic simulations, but at the same time, communication is very important. So how do organization or the people communicate? And we try to model that to simulate what really happened on that particular day. So this is a simulation of 1 hour, 2 hour, 3 hour, 4 hours, how the traffic get congested by using certain what we call agent-based model of how people are evacuating and trying to cope with that particular wildfire disaster. And trying to understand what is the importance. Typically, people in here have 2 cars every household. So they may use all the cars they have to evacuate. If they only use 1 car, it may have been much better in terms of evacuation. Now, also, if the issue as well is when cell tower or mobile phone goes down, how do you deal with it? So we model that through the communication model. Some people were trapped, so they thought they would die trapped in a parking lot. How 150 survivors of California Deadly Fire made it alive? So the people over here stayed near the Walgreens and they were trapped, but they were decided to go inside to protect themselves and trying to see how, as the wildfire goes away, they waited in a certain safe area by community talking to each other and cope with that sort of a issue. So this is where I'm coming from in terms of how do we deal with disasters. And there are two approaches. And I'm borrowing a sort of concept from a professor in psychology, looking at what they call safety 1 and safety 2. So approach 1 is managing safety by snapshots. And this is what we do all the time, actually, as engineers. We look at risk. You look at the sort of a fluctuation of the performance, the things happening on. You may put some probability functions, as we all do. And then we say certain probability, its limit of unacceptable performance. So what you do is that you create a threshold. And if you say, if it's going beyond that, you design to ensure that that accident doesn't happen, but sometimes accidents do happen. And what you do is that when accident does happen, you learn, and then you're trying to cope with a further accident. But then again, you make a mistake or your assumed failure mechanism is different. So there's an accident again, and you learn, and then you do cope with it. So it's very, very reactive in terms of how we deal with what, but at the same time, we create a lot of margins to ensure safety. And that's what we've been doing in our engineering practice, which is really important thing to do. So managing safety by snapshots. That allows us to feel comfortable about it. But on the other hand, in the past, it's too expensive to continuously monitor. You are difficult to monitor things because you don't have good sensors, or maybe you don't have good fast computers to deal with it. But now we have a lot of emerging technology which we allow us to monitor more carefully. And that's what many people are starting to do. So this is managing safety by everyday work, meaning that you monitor your things and make sure that you're within the certain things, and you learn as you monitor, because every locations are different. And you may see some divergence of things because actually your prediction or your assumption made at that time when you made your prediction was different, and therefore you can learn as you go along. And then by doing that, by continuously monitoring, you learn, but then you can anticipate and respond and trying to avoid any accidents. And GEO, I'm sure, is trying to do this right now.
Yeah.
If you know the actual performance, you can learn how to react quickly if a disaster starts to happen. You cope with a future unknown demand, because climate change, we don't know where we're going. Hong Kong is keep on developing. You don't know where the new people, where people will start to live. And how you deal with that, that's cope with a future unknown demand. The demand that you made a prediction may be different because somebody said, let's put new buildings over here, which was not considered during when the prediction was made. And then by learning, you can find any potential improvement, improved design, construction process of that. So you learn. So that's what the emerging technologies can do, is allow you to learn by monitoring things, knowing the actual behavior. Just to give you the wireless sensor network, and you can see how fast it develops. Sort of 10 plus years ago, we developed this at Cambridge. When I was at Cambridge, this wireless sensor tends for a London Underground monitoring, tunnel monitoring. 3 years later, we made a smaller one because you can see the battery was inefficient and all these things. And then a company spin out, and Wiser Innovation is part of Leica now, that it uses all these things. And now you can get a lot of data in the difficult to access sites. Well, again, 3 years later, another PhD students, 2 PhD students spin out for other one like Atterbury or 8Power. This one uses the vibration to generate energy and then use that energy to send signals. And Atterbury are ultra low power sort of a sensor system. So it's trying to use less power and prolong the life of these sensor systems. You can get variety of sensors now, like tilt sensor or miniature one, laser distance, where you shoot a laser to get the distance between the target points, vibrating wire strain gauge interface, or warning signs if you want, or cameras. So there are a variety of things, and I understand GEO is using or experimenting via these things in their sort of a slope safety management. And the technology has evolved so much in the past 10 years. For example, you can hop, 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 and go to long distance by what we call mesh network. So you can see that 750 meters, 1 kilometer, 770. So you can hop, hop, hop for 3 kilometers for certain technology. We call this LoRa devices. And GEO is trying to do this, whether they can use this in their sort of a slope safety programs. So that is one of the big achievements in the past 5 years or 10 years, trying to go for long distance. The other one is using much low power to run these systems so that we can monitor for many, many years. So for example, if you only need to take readings every hour, like temperature, humidity, or tilt, you can use a certain battery. You do hourly monitoring, you monitor every hour. You want to do that because you want to see how this particular site is sort of behaving in daily life. And you create a meshwork. Theoretically, it will last for about 10 to 15 years. Obviously, you may want to measure acceleration and wind velocity, that high frequency one, and that becomes more difficult because you have much more information in a given data. You can do a 5 selected recordings every hour, each 5 selected readings for a certain way of propagating. It takes about 1 to 2 minutes to send the data. So that requires a lot of battery energy. And if you only do 1 hour interval reading for 5 seconds, it only lasts for 40 days. So the idea is to use a trigger mode. That means that these modes, this particular sensor, when it moves, it takes a reading and sends a signal. So that will allow to save energy. Or you can use the energy harvesting devices that I mentioned. So these are the new things coming up to trying to cope with high sampling date data. The another technology I'm favor is fiber optic strain technology. This is using a standard optical fiber, but what it does is that as you shoot a light along the fiber, I can get the temperature, strain, or vibration characteristics of every, I don't know, 10 centimeters or 2 centimeters or every 2 millimeters, depending on your interrogator, for many, many miles or many, many kilometers. So I'm using American, many, many kilometers, tens of kilometers. So that means that I can get strain temperature along this particular fiber for long, long distance. And what it does is you shoot a light, and every point we call what we call backscatter light, because the fiber has some crystal which allows you to get some feasible small sort of inhomogeneity in this particular crystal, give you a small light coming back. And that small light coming from certain location has a characteristic of a temperature, strain, or vibration, which you can decompose into the frequency content of the light, frequency versus amplitude. And then for vibration, I can see how this Rayleigh peak moves up and down. I can see the Brilliant's peak moving like a vibrating wire strain gauge, shifting its frequency, give you strain and temperature. Or if I look at the certain frequency, if the temperature changes, the amplitude changes from that light coming back from different locations. And I know where it's come back from because the speed of light is constant. So if you shoot a light at a given time, it will come back at delta t. And that delta t times speed of light divided by 2 with some coefficient gives you where it came back from. And I can do that for many, many kilometers. So this is like a fiber. You can see the inner core is a fiber. This is the fiber which is in the middle, but then this is protected by these wires so you can make it a robust sensing cable. It measures strain, meaning that if you step on it, that strain transfers into this optical fiber, and that strain that you're measuring outside is equal to the strain over here, and you can measure the strain, which is equivalent to strain outside. This is a temperature cable, for example. If you want to step on it, you don't want to transfer the strain, so that means that this one has a gel. That means that this fiber, even you step on it, you don't transfer the strain, and you just measure the temperature. So you can try to get different cables to measure temperature and strain. Let's look at one of the case studies. This is a levee in Black Hole in Louisiana. And this is the Mississippi River, where we are monitoring the levee system for seepage and uplift. And what this happens, so you can see this is a Mississippi River, and there's a Red River, and this is a particular site we had a levee, which actually had a increase, this sand boils on the downstream, which I'll show you later on. So they had to remediate this particular one because they see sand boils appearing on the downstream. So here you see there's the embankment over here, and this is a downslope, and the river, Mississippi River, is over here. And you can see that the seepage has gone, and then sand boils appear on this particular part. So they had to renovate. So this is maybe a better one to see. You can see a Mississippi at flood stage, and that seepage happened, and then the flooding, the sand boil appear on here. So they had to remediate over here by putting additional overburden. So we put a strain sensing or a temperature sensor and acoustic sensor on here. So here, I'm not going to show you the acoustic sensor. We want to use this acoustic sensor for geophysical measurements over here. But I want to show you the strain sensor that was embedded vertically into the borehole. So they have a vertical boreholes where you install the fiber optic inside for a certain distance. We drill the hole and install the fiber optics. And as the seepage happens, we wanted to see how this particular ground moves up and down inside the embankment. So here's cables. This is for the installation of the surface, installing the fiber optics. And then here are some of the ones that you drilled inside, create a borehole. And then within the borehole, we install the fiber, attaching the optical fiber, and then grouting it to see how the fiber, to embed the fiber into the ground. And then we have a data acquisition of monitoring that and trying to understand. And also we did a distributed acoustic sensing, but that's a different one. I want to show you a little bit on the fiber optic strain. So this is the borehole, two boreholes where you have a data where you have a strain and then at different time. And you can see that this is up, this is top 10 meters, and then it goes down to 20 minus 15. So it's 25 meters deep, a borehole where we apply strain. And you can see that the strain is moving and actually moving up and down at different location. And this particular location represents the interface between fat clay and sand. And this is with time versus strain. And you can start to see that the strain is developing in the certain location. Now, if you look at that particular, so if you look at that strain data, which is shown, this is a relative strain change versus time. And you can see that green one is a strain, so it's developing, but unfortunately our data acquisition got stopped, so we couldn't get a data over here, recovered over here. But you can start to see how temperature, a strain is developing with time. What I'm showing downwards is the gauge height. This is the river level on the upstream side. As the river gauge level changes, you can see that the strain is responding in a very similar way. And you can see that the value over here is really small. Also, what we can do is that we can integrate the strain to get the displacement at the top and measure the displacement at the top, how it's moving back and forth. And this is shown over here. This is the displacement of the top of that instrument. And you can see it's in, this is in inch, but you can see 0.05 inch, 0.2 inch. 0.2 inch is about 2 millimeters. So you can see a movement of few millimeters but going up and down, which corresponds nicely to the river level. So I show the arrows, how they coincide, and then how it's moving. So we start to monitor the heartbeat or breathing of the levee using this system. We start to learn how it works. Here's another one that many, you can start thinking about these fiber embedded into the pavement, or 5G connection with the fiber optics for your internet connection. You can embed fibers. And what here is that we're embedding fiber in the roads, and that means that our road becomes like a sensor. And as a truck goes onto the road, we can start to monitor the strain development going over here. And this one shows that the strain and one of the cables embedded, it's strained, and then you can see the truck moving forward, where the front wheel and rear wheels are shown over here with compression and small tension, as you see over here. And you can see that particular action, and this is called 1 microstrain, 2 microstrain. Now you can walk along this fiber. So if you walk along, you can see distance versus time, and as you walk along, if you run, you have hop, 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 and you can see the hopping of this, and you can trace the movement of the person, and that gives you on the order of 0.4 microstrain. You can walk as well. If you walk, you have 2 feet at the same time, so it's more continuous. So I can tell you whether you're happy hopping or you're not happy, you're walking. And through that process, you can see how people are using the road, for example. You can listen, so this becomes a sensor of, I can have a dog running as well. And that gives you the monitoring of that as well. So what we want to see is that by embedding these fibers, maybe you can listen to wildfire, or you can listen to landslide moving, or you can listen to how people are using the road and that sort of thing, which is quite interesting technology that you see. And this is called distributed acoustic sensing technology. So I want you to remember is that by monitoring, you want to monitor what's happening in actual performance. And based on that, what you want to do is learn from experience, learn the right lessons. And then you anticipate what are the potential threats, opportunities, and you can do that for the data that you measured at the particular location that you're monitoring. And that allows you to think about how to respond. And one thing important to start looking with a community, because I think the response is not by the people like GEO trying to look after the safety of the slope, but you have to communicate with the community. So we've been working with a small community over here, Bolinas, which is having an issue with wildfire because they're surrounded by sea. And then you have the forest, which wildfire, they have only one way to exit. And this is the roadway that trying to evacuate. And one important thing that they learn is that you have to, don't use 2 cars, trying to use 1 car. But more importantly, in this particular case, communication is very, very important for that particular town. Every town is different because of the way it's being geographically location and how people live. And in this particular community, cell communication, if it's working, you have a better chance of evacuating. But if the cell communication is not working, you have a much worse chance of, because this is the traffic simulation showing how the gridlock is blocked because the communication is not working. And I know Hong Kong GEO is trying to communicate with community, and that's what we've been doing as well in terms of trying to see how people can communicate. But we do a lot of simulations. So what we want to do is that we use our simulation, using games, and we're now going digital, like what you see over here. And then, but then at the same time, they are the one who knows the local knowledge. And trying to get local knowledge from our colleagues in the residence and community allows us to improve our simulation and develop confidence in terms of evacuation. And at the same time, community learns about what's the best way, what are the options for evacuation. And then at the same time, community becomes our teachers to tell us what is the better way to do the simulations. So today I was trying to introduce emerging technologies for slope safety. It's not about slope safety, but it's really how to deal with our system, which needs resilience, which is affected by natural hazards. So GeoMonitor, what we want to show is the value of proactive actions rather than reactive actions. We want to anticipate, show the value of proactive action-based learning. We have to not just take readings, but we have to be learning from that particular activities and anticipate. And that shows the value of community engagement, because unless you know the community, it will be difficult to utilize that learning into reality. And that becomes GeoRespond and GeoAdapt, show the value for improved safety and recovery after an event. That means that if you know how it reacts to, you have a much better chance to respond and then adapt to recover from any natural hazards that you may have. That means that Geo and our community has to make a business market in smart infrastructure, trying to promote that. So we need to create a business market to build a trust with infrastructure owners and community members, and then find a framework to start this dialogue is presented by defining the values. So I'm trying to show the values of how this proactive action will be good. We want to make sure like Geo has a satisfaction and giving a sort of a happiness in terms of the operation into the workforce, and so as the people working as a construction industry, what we are doing gives the job satisfaction. And we want to make sure that we're going to monitor this for many, many years to come, because our infrastructure is going to last for hundreds of years. So in summary, my message today is, rather than just geo-monitor, are you ready to geo-anticipate and adopt and make some lessons? Thank you very much.
Thank you for Professor Soga's insightful lectures. And you have demonstrated us some using real examples, hill fire, landslide, on how to use emerging technology, including sensing technology, Internet of Things, fiber optics, to solve a real problem. In particular, the emergency services, evacuation, and communication. I think we learned a lot. And indeed, I suppose it's in line with the symposium, because we learn from the monitoring data, experiment, and using the film. And we will advance our technology using a numerical knowledge to do a better prediction in terms of debris flow in future. So thank you again, Professor Kenichi Soga. Thank you.